Hey guys, Mr. Kilgore here. Today we're going to talk about one of my favorite topics to teach, and that's gas laws. We'll just do an intro video right now. Um, so here we go. I'm here in the storage closet, recording this for you guys. So you guys are off tomorrow, but watch this before the next class and get ready. So these are some of our objectives. We're going to talk about the properties and the units and variables we're going to use to describe them. Introduce the kinetic molecular theory and its assumptions. And that's what we're going to get through today. And later, we will talk about using absolute temperature and performing calculations with these properties. So just a quick review. The different phases of matter. We have solids, liquids, and gases. Solids have a definite shape and a definite volume, meaning they occupy a constant amount of space and they hold their shape. A liquid has a definite volume, but no definite shape. It'll take the shape of the container. A gas is very different. Gases are very different from solids and liquids because they don't have a definite volume and they don't have a definite shape. They expand to fit their entire container, no matter what the container is. If it's a room or a jar or a flask. So let's move on. So write that bold point down, gases, the main definition there. Properties of gases. We're going to talk about these. You guys are going to want to write this down too. The first property we're going to discuss is volume. Volume. The variable we use for volume, the letter that we use in equations, is V. Nice and simple. Volume represents how much space the gas occupies. The units that we're going to use are liters, milliliters, meters cubed, centimeters cubed. Those are the ones we use in our class. There are some other ones. We're going to stick to the metric units, though. You could have kiloliters if you want, or megaliters, or microliters. So all sorts of different volumes, units there. Pressure. Now, this is one that you may have heard of before, especially if you watch the weather. If you find a unit you have no idea what it is, it's probably a unit of pressure here. So the pressure is the force caused by the particles colliding. So the physics definition is pressure is force over area. So the units we're going to use are atmospheres, kilopascals, and millimeters of mercury, mmHg. So I know that seems a little funny. You see millimeters here. We're going to get to what that means later in this video. So write these ones down and moving on. You can pause it, obviously. Write it down at your leisure. The next property is one we've talked about before, temperature. We talked about that when we went over energy. Temperature measures the average kinetic energy of the particles. Kinetic energy being energy associated with motion. The only temperature unit we use in gas laws is Kelvin. We have to use that because Kelvin temperature is absolute. So how we get there from Celsius? All we do is add 273, just like we did the last unit when we talked about energy. Okay. Last one you're familiar with, moles. Moles measures the number of particles. So, and the worst abbreviation for unit, MOL. That's the unit for moles we're going to use. Oh, and the variable is N. So keep that in mind as we move on. Know your variables and know your units. All right. So quick recap. Here's a PVU table. Property volume, variable V, liters, milliliters, meters cubed, centimeters cubed. Those are the units we're going to use in our class. Property, pressure, variable P, nice and easy. Units, kilopascals, kPa, atmospheres, atm, millimeters of mercury, mmHg. Temperature, variable T. Only unit is Kelvin. Moles, variable N, unit moles, MOL. So the kinetic molecular theory is the kinetic, meaning motion or movement, molecular, meaning particulate, the particles. So I abbreviate it KMT, kinetic molecular theory. These assumptions will help us understand the properties of gases and the effects on changing those properties. So the assumptions of the kinetic molecular theory are that particles are in constant motion. The particles are always moving. Big misconception is that particles in a solid do not move. But actually, they are just vibrating, but they're vibrating in place. Um, Absolute temperature, Kelvin temperature, directly relates to the kinetic energy. So the higher the temperature, the faster those particles are moving. The lower the temperature, the lower they're moving. If you get to absolute zero, they theoretically stop moving. Particles have perfectly elastic collisions. That means that no energy is lost when the particles collide. Now, if you had a perfectly elastic collision with a bouncy ball, you would drop it, and then it would bounce back to the same spot all the time. However, well, that doesn't work in there. So, because eventually it would damp the height and stop bouncing. Also, the last thing is particulate volume is negligible, meaning we can actually ignore the volume of the actual particle because it is less than 0.1% of the overall volume of a gas. So gas is about 99.9% empty space. So most of the gas is the space between the particles. Okay. So wherever you're surrounded by the atmosphere, you're actually being constantly bombarded with gas particles. So we don't feel them normally. We normally only notice them when there are changes in pressure. You'll notice sometimes when you're driving up a hill, your ears might pop. That's because of changes in atmospheric pressure. Or if you have a big difference in pressure and you're in between that, you might notice wind. Those are gas particles moving because of differences in pressure. And if you guys are ever in an airplane, changing that altitude, at higher altitudes, there's less atmospheric pressure. So a lot of times your ears will be sensitive to that. So atmospheric pressure is just the pressure exerted by the atmosphere around you. There's a instrument called a barometer, which measures atmospheric pressure. We used to have one here, but it had mercury, so we had to get rid of it. Right now, we're under a large column of air. There's a lot of air on top of us. You might notice that if you go very deep in a pool, you might feel the water pressure on top of you, mainly in your ears. And that's because, well, there's a lot of water on top of you. It causes a lot of force on an area. So that's what pressure is caused from. Essentially, we are under a column of air. There's a lot of air on top of us. And that's what causes atmospheric pressure. And the average pressure at sea level is 1 atmosphere. And that's where we get that term, 1 atmosphere of pressure for standard pressure. The higher you go up, the higher the altitude, the lower the pressure is. And that's one of the interesting things. If you ever look on some of the brand mac and cheese or brand pastas, they have different cooking instructions for high altitude. And that's because the atmospheric pressure is much lower at those high altitudes. Or you might see if you ever have a pressure cooker, you have a pressure cooker, it cooks at a higher temperature because it's cooking at a much higher pressure. So those are some interesting things about pressure. And if we change the pressure, other factors will change as well. And we're going to get into that in later lessons. Measuring pressure, the first guy that really measured pressure was Torricelli, and he came up with the Torricellian barometer. Now, we use mercury because mercury is a very dense liquid metal. He filled up a barometer, basically a tube, with mercury, inverted it, turned it upside down in a pool of mercury, and the level of the mercury went down in the tube to 760 millimeters. So that's where they have the term millimeters of mercury. Standard pressure is 760 millimeters of mercury, meaning the atmosphere pushing down the air on top of us is enough to support that mercury 760 millimeters, that weight of that mercury. And that's where we get the term millimeters of mercury. It is literally the height of mercury that can be supported in a column by the air. So there's another diagram illustrating that. And that's it for today. Next class, we're going to do the gas law simulation, and we're going to look at some of these things. It's a PHET simulation. So get ready for that, guys. Looking forward to it.